So let's take a look at how to apply quadratic functions to a real-world situation. In economics, we can talk about revenue. And revenue is simply the amount of money that you receive for selling a product. So if you have X products and you have P as the price per product, you can multiply those two, and that will give you the revenue. Now, if the price of an item increases, well, higher price means that you're going to sell less. Likewise, if the price goes down, then you'll sell more. That relationship between the two, the number of items sold and the price of the item, that is called the demand equation. Here we have an example where a business is selling recumbent bikes, and the price is P dollars and the number of recumbent bikes sold is X. The demand equation is given by X equals 18,000 minus 200 times the price. So if we want to find an equation that models the revenue, we know that revenue equals X times P. And we're told that we want our function to depend upon just the price. So R equals, well, we can substitute our understanding of what X is based upon the demand equation. And so we get 18,000 minus 200 P times P. So this X value is just simply getting replaced by this from what we know from the demand equation. So what is the domain of R? Typically, we would think that a function like that, 18,000 minus 200p, all times p, is going to be all real numbers. But we are expecting revenue to not be negative. So let's think about when it would equal 0. That would be the lowest revenue we would allow. So 18,000 minus 200p times p is our revenue. When does it equal 0? Well, we have two factors multiplied together to give 0. That's only true if one of two things happens. 18,000 minus 200p equals 0, or p equals 0. So if we solve, we get p equals 90, or p equals 0. Now, it's quite easy to tell that if p is negative, that our revenue is going to be something times a negative number. And it'd be 18,000 minus a negative, so that'd be 18,000 plus something. This would be a positive number times a negative number. So P can't be negative. And that makes sense. Price can't be negative. Now, if P is above 90, what happens with a very high price? With a very high price, say P equals 100, we would have a negative number times a positive number. And again, revenue would be negative. So our price has to be between $0 and $90. So the domain of our function is going to be between 0 and 90. Now, what would be the unit price to maximize revenue? So again, we had R equals 18,000 minus 200p all times p. That is a quadratic function. Let's write it as such. We have negative 200p squared plus 18,000. Now, if we were to graph this, this would be a parabola. The maximum of a parabola comes at its vertex. So h equals negative b over 2a will be negative 18,000 over 2 times negative 200. And this is going to be 45. So the unit price that corresponds to a maximum revenue is $45. if that price is charged, what's the maximum revenue? Well, we've already said that R equals negative 200 P squared plus 18,000 P. So let's evaluate R at 45. So we have negative 200 times 45 squared plus 18,000 times 45. This yields for us 405,000. That's a revenue, so the maximum revenue is in dollars, $405,000. Now, how many recumbent bikes are going to be sold at that price? To answer that question, we go back to our demand equation. So X is the number of recumbent bikes sold. So we will take 18,000 minus 200 times that price of $45. And so we get 900. So the answer would be 900 recumbent bikes. So now we're going to graph R, and we're going to use Desmos to determine how much should be charged in order to ensure a minimum revenue of $360,000. So let's go ahead and graph our revenue. So now to graph this function, we will go ahead and plug in our values. And let's go ahead and I'm going to move this so that it's more easily seen. And now, how do we know what our domain and range should be? Well, let's go ahead. We know that the minimum that X should be is 0. And then we know our maximum is 90 for our domain. And then our minimum revenue should be 0. And then, because revenue can't be negative. And then we know our maximum revenue, we've already said, is going to be $405,000. And so now we see the graph of our revenue. Now the question is, how do we ensure that our revenue is going to be at least $360,000? So let's graph y equals 360,000. And now you should see, if you click on the graph, two key values. We want our revenue to be at least 360,000, so our revenue is above 360,000 on the interval from 30 to 60. So when our price is $30, or when our price is $60, our revenue is 360,000, and when it was between, our revenue is above. So there is our answer. It should be between $30 and $60. So the revenue will be at least 360,000 when the price is between $30 and $60. Now let's look at another application. Here we have a rancher who has 600 yards of fencing and wants to create a rectangular corral. So we have a rectangle, and we know that there are 600 yards of fencing. So that means that the perimeter, the distance around, is going to be 600 yards. So let's call this x and this y. And so 2x plus 2y must equal 600 yards. Now we want to know about the area. Well, area of this is going to be x times y, the area of our rectangle. So if I let a be a function, a is going to be x times y, but that's too many variables. So let's go back up here. 2x plus 2y equals 600. So this means that 2y is going to be 600 minus 2x, and then we can divide everything by 2. So y equals 300 minus x. And we can take that information about y and substitute it into our formula for our area. So our area equals x times 300 minus x. So A will equal 300x minus x squared. So A equals negative x squared plus 300x. To maximize this, notice this is quadratic. Its graph will be a parabola. It opens downward. Therefore, the vertex will sit at the top of our parabola. And so we just need to find our vertex. So h will equal negative b over 2a. So that will be negative 300 over 2 times negative 1, which is going to be 150. So that is the x value of our vertex. Now, what's that mean? That means that our area has a maximum. Notice our parabola is opening downward, so our vertex is at the top. So that vertex, that maximum, is obtained whenever x equals 150. So that means that x equals 150 is the maximum here, or that yields the maximum. Now if y equals 300 minus x, that means that y will equal 300 minus 150 at the vertex. So y equals 150. Now, the y there is not on our coordinate plane. The y here is in relation to this. So our area is a maximum of 150 yards times 150 yards. So what are the dimensions that will enclose the maximum area? 150 yards by 150 yards.